Windows enforces strict boundaries on user mode applications. A standard process is restricted. It cannot access hardware or read kernel memory directly. To interact with the operating system, an application must use documented API functions exported by standard libraries, specifically kernel32.dll and ntdll.dll. These dynamic link libraries serve as the mandated bridge to the kernel. Every legal application routes requests through these exact pathways. If a program needs to allocate memory, it uses this specific channel. This predictable routing creates a choke point. Execution flow can be intercepted and redirected right before crossing the kernel boundary. Because a user mode application lacks an alternative pathway to the kernel, it must rely on the integrity of the data returned by these libraries. By controlling the boundary, an attacker filters the specific system state information available to the application. Intercepting calls to operating system functions by modifying the call path is formally known as API hooking. It is not inherently malicious. Legitimate security software and debugging tools routinely install API hooks to monitor process behavior and enforce system policies. However, rootkits and banking trojans abuse the exact same mechanism to capture keystrokes, intercept network traffic, and hide their presence. An attacker achieves evasion by intercepting the legitimate API response, modifying the return values, and handing the falsified data back to the calling process. When the core routing mechanisms are compromised, an attacker can redirect execution to any memory address within the process space. The host application follows these redirected paths without detecting the deviation from standard execution. The critical issue for defenders is that user mode forensic tools rely on the exact same native APIs as the malicious applications they attempt to analyze. If malware successfully hooks the API, it dictates the data seen by the forensic tool, obscuring malicious artifacts from standard analysis. Every portable executable binary contains a foundational structure known as the import address table, or IAT. Because a program doesn't know where system functions will reside in memory until it runs, the IAT acts as a static map. It stores the dynamically resolved memory addresses of the binary's imported functions. This chart shows the normal state of the IAT. The function name correlates directly to its real memory address. In IAT hooking, malware overwrites the legitimate address for a target API with its own malicious memory address. This technique requires absolutely no code patching. The executable instructions of the API remain entirely untouched, making it mechanically clean and simple to deploy. By changing this single static pointer, the trust chain for that specific function call within the host process is entirely compromised. Let's trace the execution path when a compromised application calls a function like CreateFileA. The application consults its import address table, blindly reading the manipulated pointer. Execution jumps directly to the malicious handler function instead of the legitimate operating system library. The real CreateFileA in the kernel32 library is bypassed during this initial jump. It never executes. However, IAT hooking has a significant architectural limitation. If the host process reloads the DLL, the operating system flushes the IAT, replacing the malicious pointers with the correct addresses and removing the hook. Furthermore, an IAT hook is ineffective if the host process bypasses the static table and resolves API addresses dynamically at runtime. While IAT hooking is a mechanically clean exploit, its reliance on static tables makes it rigid. Any process that avoids the IAT ignores the hook entirely. Attackers bypass these limitations using inline hooking, a more aggressive alternative to static pointer manipulation. Instead of altering a lookup table, inline hooking directly modifies the executable code bytes in memory at the target function's address. This left block shows a standard Windows API prologue. These opening instructions are prime targets. Malware overwrites the first 5 bytes with a relative jump instruction, pointing to its own malicious code. This absolute modification forces the CPU to jump to the attacker's payload the exact millisecond the API is invoked, regardless of how the application found the function address. Overwriting executable memory directly makes inline hooking a more effective technique, as it catches all calls to the API, including direct dynamic resolutions. Destroying the prologue instructions introduces a severe mechanical problem. Without those setup bytes, the legitimate function cannot execute. If the malware needs the original API to complete a task, the process will crash. To solve this execution block, malware authors utilize a trampoline, a small, dynamically allocated code stub containing the stolen bytes. Execution takes 3 steps. First, the application hits the hook. Second, the hook processes data and jumps to the trampoline, executing the saved bytes. Third, the trampoline jumps back to the unpatched remainder of the original API. By executing the stolen setup bytes in isolation, the trampoline preserves the original call stack and allows the system library to run normally. The trampoline mechanism allows malware to intercept the data and modify the system state, returning execution to the host while maintaining the appearance of normal operation. We can see this mechanic applied practically by looking at NtQueryDirectoryFile, a critical native API responsible for system-wide directory enumeration. This is the foundational call underlying Windows Explorer, command line searches, and forensic directory listings. When a user asks what files are in a folder, this API fetches the answer. If a rootkit successfully installs an inline trampoline hook on this specific API, it gains control over the system's file visibility. When an application queries a directory, the original API function completes its read of the hard drive and hands the true unfiltered file list back to the hook. On the left, the API returns an array containing file A, file B, and the malware's file. On the right, the hook intercepts the data, scrubs the malicious file completely, and hands the filtered array back to the command prompt. The hook code explicitly parses the array, matching file names against its own components, and deletes those entries from memory before the user ever sees them. The manipulated list is passed back to the calling application with a standard success status. The system throws 0 errors. The file remains on the physical sectors of the disk, but it is absent from the memory buffers returned to the user. The rootkit achieves evasion by ensuring its artifacts never appear in the data structures reported by the operating system. Defeating these hooks require analysts to abandon their reliance on standard APIs. Detection depends on comparing expected static baselines against the live memory of the system. To find IAT hooks, a forensic analyst compares the live IAT pointers loaded in memory against the original import address table found in the binary on disk. Any mismatch reveals a compromised pointer. Inline hooks require a different approach. Analysts scan live memory to read the first 5 to 8 bytes of critical system functions. In this hex dump, an E9 opcode, a jump instruction, is sitting exactly at offset 0. A JMP or call instruction occupying the very first byte of a system API is the definitive, undeniable mechanical signature of an inline hook. Memory scanning frameworks such as Volatility and its Malfind plugin automate this process. They parse process memory to identify these exact executable anomalies. Security analysts use these tools to actively sweep the memory landscape, forcing deeply embedded hidden execution pathways into the light. Detection relies on identifying these mechanical deviations in memory. While behavioral heuristics or system logs may overlook the presence of a hook, direct memory analysis exposes the modified instructions, bypassing the potentially compromised API responses. During dynamic debugging in a tool like x64db, analysts will set strategic breakpoints directly on heavily abused APIs like CreateFileA and virtualalloc. When the breakpoint hits, the analyst must actively trace the call stack backward, stepping out of the API to identify the true memory region where the execution flow originated. API monitor tools apply a similar principle at scale, capturing thousands of process calls and filtering for executions that lack a legitimate, disk-backed caller in the stack trace. API hooking weaponizes the intended design of Windows architectural routing to gain control over process execution. Relying on high-level administrative tools is insufficient for incident response. True defensive capability requires an analyst to understand and verify execution flow at the byte level.